Hi, class. So, one popular way now of improving the realism of your animation is to simulate the real world, basically physics and kinematics. Kinematics, of course, are the laws of motion. Um, so, we can achieve realism procedurally by simulating the real world, the physical world. This is actually similar to rotoscoping, right? If you want to see a ball bounce on a hill, take a video of it and trace it. We're getting the real world to tell us. So this is one step further where we actually implement the mathematics behind how we think the physical world should work. So we learn about the laws of motion, we learn about physics, we can think about collisions, for example, what happens when things bump together. We can add other forces such as gravity, and so on and so forth. You can think about a whole range of forces and properties of the real world that will matter. Now, when we do a physics simulation, it's very commonly done with a particle system, but the properties we have to give objects include velocity. We've seen this before, right? In some of my previous examples, we've seen how we can model how things should move by adding in a velocity and an acceleration. We can also add mass, moments, if you're good in your physics. You can also do things like object tearing or shattering. What happens when should things break, and maybe we can create new geometry. It's a very exciting part of computer animation. And I'll finally add that this could be frame-based. Let's try that again. This could be frame-based, which is what we'll cover now. But if you're doing it live, like in a video game, that wouldn't be sufficient for the same reasons we've already learned. If you're doing it live, you'd have to be time-based to be adaptive to different frame rates and things like that. Okay? Because, physics in the real world is time-based. Now, when you look at a physics system, you often hear people talk about physics and they go, "Oh my, that's really hard." In fact, when graphics cards first became popular, a few companies released physics cards that were meant to take off, and they haven't really taken off in the same way. Cards dedicated to processing physics calculations. Now it seems like it's either done on the CPU or offloaded to the GPU if they can manage to do them in linear algebra. But that's a whole different topic. But the point I wanted to make is there's a whole continuum here. We have, at the very left, you can have simple approximations, right? So you can actually do very simple things all the way up to a full physics system. And if you work with like astronomers, I can't spell today. If you work with like astronomers or physicists, you'll actually get very professional systems that are about simulating physics, so it can get very, very complicated and very serious. So I'm going to start by jumping into some demos. So I wrote this up actually yesterday, so it's not been that well tested, but I think it works close enough for what we want to show here. So what I've done is I've made this this particle system where we have a bouncing ball moving around a scene. What I've done is I've excuse me, I've specified a few properties. So I have a bounce loss. When when a ball bounces off something, it loses some energy, so it doesn't bounce forever. I have gravity, which is a vector, which is 9.8 meters per second squared, and I have a small correction factor in there because how big is 1 pixel? Well, I made it so that there are 100 pixels per meter. Only thing matters is how much speed the ball has. So that's not a big deal. I've given the ball a radius. And gravity we can turn on or off. So the way we implement this, I'm going to skip the ball class for a minute and run into my setup, size, color mode, all the normal stuff. In Draw, all I do is I go through each ball, I tell it to update, move and collide, and when that's all done, I go through each ball again and I draw it. This should look familiar from all the particle systems we've done. And then what I've done is mouse pressed, mouse drag, and mouse release. You create a vector, and I make a new ball with that vector. So you can actually sling balls. You can drag the mouse and click, and let go, and the ball will fly in the direction you're moving at the speed you're moving. That's all. I also added some mechanism for random balls. So we have a system where I can add balls to the scene. But what happens with those balls? Let's look into the code. Draw is really simple. It's just a fill and a stroke and a circle. And then I have this code that says move and collide. And what we do is first we check every other ball against us. So this is me. I'm inside the ball. This is inside the class. When I'm moving, I check every other ball. Hey, am I colliding with you? Okay, that's n squared. That's not going to be fast. And then I go, if I have gravity, I add the gravity to my velocity. Then I add my current velocity to my position. I make sure I don't go across the walls. So if I hit a wall, you can actually just invert the, if I hit the side wall, I can bounce up by inverting the x velocity. Don't worry about it. But I check the wall collisions and invert them. We did this in 1010, so some of you might have already seen this. Here's the hard part. How do I tell if two balls collide? Well, that's the easy part. How did I tell if two balls collide? What's the distance between them? Is it less than their radii combined? Yes, right? So here's my delta distance, delta between them. I calculate the distance, and I compare that with two radiuses. Yay, I have a collision. And I'm not going to go into this. You can open a physics book or a basic graphics book and derive this. But I make sure, because what'll happen is you have balls coming in, and they go, and then by the time you check the collision, there's actually an overlap because of their velocity. So the first thing we do is we move it back out. No, you're rigid, you move it back out. So I move it back out, I calculate, so this will be my collision vector here. I calculate the tangent between the two circles, and then I combine their motions and project them onto my tangent, like again. It makes sense, it's simple linear algebra, a few dot products and subtractions. You might want to optimize that out as a normalize in there, okay? Same here. But that's a problem for a different day. Okay, and then we just update our balls. So each frame, the balls, they move like physics. They add the velocity adds, the gravity gets added to their velocity gets added to their speed, but we also check collisions and modify their velocity based on those collisions. Okay, basic physics system. So here's a ball. I clicked it, it's moving in space. Let's do that again. See, now it'll bounce, really cool. And because I've added that factor at the top, bounce loss, it'll lose 10% of its velocity every bounce. Now remember, that's compound. That's not linear. So it won't take 10 bounces to slow down. It'll go from 100 to a 90. Now 10% is 9. 91. Now minus 9. Instead of 90 minus 81. Yeah, it'll slowly decrease, and that 10% will shrink, which is how the real world works. So yeah, so this is a really nice physics system. I can push spacebar to turn on gravity, and now you see that gravity's pulling on it, and so it doesn't just bounce not freely. Gravity's pulling on it, and it'll eventually settle down at the bottom. Okay, that's really cool. I like to take gravity off, and it keeps going. Now I can add a second ball. Look at that, and they collide. That's really cool. So this is a physics system, and what's really nice about this, like the other particle systems we've learned, is with some code, the collision's kind of tricky, but the idea is really simple. You get this really nice pattern emerge where you can do really complicated things that we're not solving globally, we're just solving locally. Now, like I said, I didn't really test this too fully, so it's probably going to break at some point. I know that it'll break if I add too many in here, because if there's too much weight, the gravity pushing down doesn't get compensated to push up, the things aren't rigid enough. But yeah, we can add this. How cool is that, right? Now, at the bottom here, what I've done is I've counted how many balls are in the scene. Because it's an n squared computation, now it'll tell you how many calculations it takes to check for collisions each frame. And it's doing this 60 times a second, remember. So now, at 26 balls, let's make it 1,000. There we go. At 32 balls, 32 squared is 1,024, powers of 2. We now do 1,000 checks each frame. Cool. And you can do really fun stuff, like, now that I'll turn gravity off and I'll smack it. Yay! Right? And you can do that and turn gravity back on. Clunk, 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 clunk. So this is a really cool, really simple physics simulation, a really simple particle system with collision and gravity. By simple, I mean, like, this is a very reasonable assignment for you, but just beyond the scope of this course that I'm going to make you do. Let's just play with it for a second. I'm going to do two things. I'm going to make my canvas bigger, and I'm going to make the balls smaller. Let's make them size 10 maybe? How's that look? I want to add lots and see where it breaks. Okay, so it still looks good. It now looks more like a particle system instead of a bunch of pool balls kicking around. Let's add gravity. Now I have a new button. If I hit the plus key, it'll add 20 random. There we go. So now I have 41, 61. You can see at the bottom here, it tells you how many balls I have. 90 balls. Okay, we're still going good. So at 310 balls, now I'm at about 100,000 checks a frame. Looks really nice, right? Cool. And now I hit spacebar and I can play pool here or whatever. You can imagine this is a really cool video game. Turn gravity back on. All right. So I'm at 500 balls. This is a pretty beefy computer. It's a modern gen Intel i7. Oh, look. There we go. It's starting to break. Oh, it's trying to solve. Maybe it did solve. Cool. Turn off gravity again, and I can smack it. How cool is that, right? Very emergent. But let's see how far I can go with it. Oops. I erased them. Okay. Wrong key. So now I have 500 balls. Looks good. At 1,000, I'm starting to do about 1,000,000 checks a frame. Let's turn off gravity so we don't have that breakdown down there. Look at that. And now it's starting to slow down at about 1,200 particles, 1.6 million checks. So I can get, now it's really slow. So with this system, just brute forcing it, this system, I can only get about 2,000 particles, which is pretty embarrassing. This is not a lot of particles. Part of the bottleneck is in how I'm rendering them as a bunch of circles. That's not fast. But I imagine that the fact that it's an n-squared calculation, where we're doing 2,000 particles requires almost 4 million checks. That's, what we can expect to be slowing us down. There's gravity. Look at that. And then, yeah, gravity's crushing and overcoming their ability to push out, because all the gravity pushing down on everybody is so much weight. Cool. What I was going to say was one of the first things I would do if I was trying to optimize this is try to break. We can do the square rooting, we can do the drawing. All this stuff is slow, but it's that n squared you want to attack first. How would you fix that n squared? Well, we could just use a quad tree. And if I have a quad tree implemented, then each ball would only have to do a neighborhood check of are you close to me? Yeah, you're close to me. Hey, did we collide? Anyone that's not close to a ball, you wouldn't have to check. So you could really break down that n squared complexity to much smaller complexity with a quad tree. Cool. So this is a physics system. Download and play with it. It's a lot of fun. I'm going to undo those changes I made and save that. All right. Yeah, I also wanted to demo another program. This is really fun. This is something I did during my postdoc a million years ago, which is funny that it worked out of the box. This is one nice thing about Java. I haven't touched this in about 15 years. I just opened it and pushed run, and it worked. Interestingly, in those days, I used processing to get as the screen renderer, okay, which is kind of fun. So what are we looking at? There's 4 fireman robots here. So here's my problem I had. My problem was this. I wanted to see if robots could help me move like a piece of cloth, like a table, but less rigid. It was a general problem I was curious about. And my supervisor said, it won't work. Robots you need global tracking. I said, no, we can do it locally. So instead of spending 8 months to implement it, I prototyped it. I came up with a simulation for a cloth here. This is a cloth simulation. And these robots are little programs, and all that they have access to is the pressure at their corner point. They don't have a direction, they just have a pressure. How much is it pulling? And the question was, is that enough information to solve? And this is me with my 2 hands. So if I pull, you can see that the robots will move to normalize that pressure. And then I can turn. I ended up getting a job, this one, and didn't implement this. But this was I showed this to my team, and they're like, oh, maybe it will work. Maybe it is enough information for the robot to decide. So this is a cloth simulation. Like the previous one, it's actually a particle system, an n by n, but we implemented the physics of cloth, stretchy cloth, where between the points you solve, it's called a mass spring model. You solve for how stretchy and rigid it is simultaneously, and you do that appropriately, and you get this nice cloth model. Now, the thing about physics models is that they're not stable. They're really hard to get stable. In the previous example, we saw when it broke, and the same thing's going to happen here. Bam, it exploded, right? So you got to be careful with physics systems. I wanted to show that. Let's see. I have a slide. Let's go over to my slides. Cool. Okay. So here's an example. This is an open source library you can actually download for your phone. It's really fun. Here's an example of how far you can take this. This is called Liquid Fun. This works on phones. So this is classic physics here. You know, boom, boom. This looks kind of cool. But then they go putting in massive particle systems. So this is a semi-rigid system, kind of like cloth simulation. And then there's this poor emitter, and you see that we'll talk about this in a bit, but this is a ragdoll model for the person. You can do all kinds of really cool stuff with particle physics, particle systems and physics. A lot of fun. You can do liquid simulations. Of course, they're bragging about particle lifetimes. We've talked about that. You can have multiple emitters. This poor guy. Right? There are fewer bugs. Yeah. Like I said, it's not stable. It's not stable. Fewer. They didn't say it's bug-free. It's a physics system. It's not going to be stable. You're going to find instabilities. Cool. So that's all I'm really going to talk about with physics systems. This can unlock. This is all I'm really going to talk about with physics. We'll come back and learn about hierarchical modeling in a moment. But I just wanted to show you that when you take particle systems, you can put in physical properties as a way to solve your problem, add realism, and support your animation procedurally instead of having an animator do it.